So hello everyone, welcome to my presentation. So as Jason introduced, I'm Gong from Duke University. First of all, my students are supposed to be here to present this paper. However, they have graduated and they cannot make it to the conference. So I'm here to present our work. So as you know, in federated learning, we are given some clients. These clients could be smartphones, IoT devices, self-driving cars, and so on. Each client has some training data locally. And we also are given a cloud server. The cloud server maintains a machine learning model called global model W. Each client also maintains a machine learning model locally called local model. In federated learning, these clients jointly train the global model W iteratively. And in each training round, federated learning performs the following 3 steps. In step 1, the server sends the current global model to the client, or a subset of them. In step 2, the client trains their local models based on the current global model and their local training data, and then send their local model updates to the server. Specifically, client I can initialize its local model WI as a current global model W, and then uses stochastic gradient descent to iteratively update its local model. After training the local models, the clients send their local model updates to the server. In step 3, the server aggregates the client's local model update as a global model update and uses the global model update to update the global model. Different federated learning algorithms essentially use different aggregation rules in step 3. For example, in FedAverage, developed by Google, the global model update G is the average of the client's local model update. And the global model W is updated using the global model update G. Here, alpha is the learning rate. So federated learning basically repeats these 3 steps for many training rounds. As you can see, federated learning is essentially a distributed system. Due to its distributed nature, it is fundamentally vulnerable to poisoning attacks. In particular, an attacker may have control over some malicious clients. These malicious clients can arbitrarily poison their local training data, which are known as data poisoning attacks. These malicious clients could also directly manipulate their local models or local model updates, which are known as local model poisoning attacks. Eventually, the global model is poisoned, and the poisoned global model makes incorrect predictions as the attacker desires. More specifically, the malicious client could be genuine client compromised by an attacker, like stealing their username and password. So in these attacks, an attacker has access to some genuine local training data. These malicious clients could also be fake clients simulated and injected into a federated learning system by an attacker. In these attacks, the attacker does not have access to genuine local training data. By the way, in my talk, I will just give you some example references. Okay, more references can be found in our paper. Depending on the attack goal, poisoning attacks can be untargeted or targeted. In an untargeted attack, an attacker aims to reduce the overall testing accuracy of the global model. In a targeted attack, however, the attacker aims to only misclassify attacker-chosen target input, while the predictions made by the poisoned global model for non-attacker-chosen input are unaffected. These attacker-chosen target input could be some specific clean input, For instance, an attacker may just want the poisoned global model to misclassify a particular clean stop sign image as a speed limit sign. The attacker-chosen target input could also be any input embedded with an attacker-chosen trigger. For instance, an attacker may want the poisoned classifier to misclassify any input embedded with a white square at the center as speed limit sign. By the way, these attacks are conventionally also known as backdoor attacks, which have been discussed extensively in prior talks. To defend against these poisoning attacks, in federated learning, people have explored both prevention mechanisms and detection mechanisms. Prevention basically means redesigning the federated learning algorithm or system to prevent malicious clients from poisoning the global model. And one category of prevention methods is known as Byzantine robust federated learning, which uses Byzantine robust aggregation rules instead of the mean aggregation rule in Fed average. Under some assumptions, these methods can guarantee that the global model does not change much when some clients become malicious and perform poisoning attacks. Another category of prevention methods is known as probably robust federated learning, which can provide even stronger guarantees. More specifically, these methods can guarantee a lower bound of testing accuracy, no matter what poisoning attacks the malicious client perform. However, a common limitation for all these methods is that they can only prevent a small number of malicious clients from poisoning the global model. Therefore, people also explored detection mechanisms. Here, detection means detecting malicious clients during or after the training process. However, after detecting the malicious client, the global model is usually already attacked by poisoning attacks. So we need to recover the global model from the poisoning attacks. A naive baseline recovery method is to train from scratch, which means you just remove the detected malicious client from the federated learning system and train a recovered global model from scratch. This method is accurate. However, it incurs a lot of computation and communication overhead for the client because it involves the client again during the recovery process. Our idea is still to iteratively train the recovered model. However, instead of asking the client to compute their model updates again during recovery, the server estimates the client's model update and uses the estimated model update to learn the recovered global model. More specifically, during the original training process, the server stores the client's model update and the global models. And then during recovery, the server uses the stored client model updates and global models to estimate client model update, okay, instead of asking them to calculate them again. Recall that federated learning performs these 3 steps in each training round. So in our method, during recovery, the server still iteratively trains the recovered global model. However, the server does not need step 1 nor step 2 in most cases. Instead, the server estimates a client's local model update GI using the historical client local model update and the global models stored during the original training process, and then updates the recovered global model. However, when the server thinks its estimated local model updates are not accurate enough, it uses client step 1 and step 2 to involve the client to compute exact local model update. Technically, we can estimate a client local model update using the well-known Cauchy mean value theory, which we probably have learned in advanced calculus class during college. This term is a model update for client I in training round T during recovery. This term is the model update for client I in training round T during the original training. This term is an integrated Hessian matrix. And this term is a recovered global model in training round T. And this term is the original global model in training round T. So I'm not going to talk about more technical details, but they can be found in our paper. Theoretically, we can show that under some assumptions, our method can recover the same global model as trained from scratch, but saves a lot of communication and computation cost. Next, I'm going to show you just one empirical evaluation result, and more results can be found in the paper. And these results are obtained for untargeted attacks. When there is no attack, the global model is pretty accurate. Now let's suppose we have some malicious clients which perform poisoning attacks, and then the accuracy of the global model reduces a lot. Now suppose we can somehow detect the malicious client and remove them and train a recovered global model. If we use train from scratch, the learned global model, the recovered global model, is accurate again. However, it incurs a lot of computation and communication cost for the client. Our method can recover a model as accurate as trained from scratch, but it saves up to 75% of computation and communication cost. So in this talk, we basically show that we can recover from poisoning attacks in federated learning both efficiently and accurately. One limitation of our method is that it requires the server to store the client local model updates and global models during the original training. So it incurs some storage overhead for the server. And this is especially challenging for training large machine learning models like ChatGPT or GPT-4. Okay? However, we can also argue that federated learning may not be a good choice to train large machine learning models on resource-constrained clients anyway. So that concludes my presentation.
So thank you very much. And Neil usually give classes runs over time, right? Okay, so that's why let's put it offline.
Okay, sure.
Yeah.